Right. For the class today, I'd like to start chapter 2. Chapter 2 starts with logic. Okay. We're going to talk about logic and what's the basic thing of logic. I mean, we're going to be talking about statements today. And statements are sentences that we're going to be trying to prove. Okay. So logic is it's essential, right, to mathematicians. It's essential when we write proofs. We want to remember the goal of writing a proof is you're trying to convince somebody that a statement is true. Okay, and if you don't use logical arguments, then you haven't really convinced them. Okay, so we're going to build the logic that you're going to use in all of your proofs to write proofs and convince people to think they're true. Okay, so chapter 2, logic. Okay. So the book kind of describes logic. Let me borrow this thing. The first sentence, it says, logic is a systematic way of thinking that allows us to deduce new information from old information and to parse the meaning of sentences. So, I like that. It's just, it's a way of correct thinking, and so if you're using that correct thinking, then the proofs that you develop are going to be correct and actually do their job, actually convince people. Here's in the book you talk about the fact that we use logic every day. I mean, hopefully you use logic every day to you have information, you make a logical decision based on the information you have, make a correct decision, and then you can develop new information. So here's a simple situation. Somebody asked me. Say somebody asked me, were you born in Ohio? And I answer them, I was born in Columbus. Okay? And that seemed to satisfy the person. Okay? Did I answer the question directly? Did I tell them I was born in Ohio? No. So this person had to use logical reasoning to come to the conclusion that I was born in Ohio. So what are the kind of, you kind of do those kind of things. You can imagine this kind of similar situation happening in any given conversation. You have to use logical reasoning to deduce new information from old information. I didn't say that I was born in Ohio. I said I was born in Columbus. Okay? But this person probably used this line of reasoning. Okay? Well, I know Columbus is a city in Ohio, and I know that he was born in Columbus. Therefore, I can conclude he was born in Ohio. Okay, so that's kind of the idea of logical reasoning. Okay, so Columbus is in Ohio. He was born in Columbus. Therefore, he was born in Ohio. Okay? So that's the idea of logical reasoning, getting new information from old information. Now, the book also makes a distinction in the fact that we've used correct logic to deduce that I was born in Ohio, but it's only, we used correct logic, but we didn't, it's not necessarily correct information that we deduced. In fact, I wasn't born in Columbus, so I lied. I wasn't born in Columbus. So, but my logic is still sound. If I say I was born in Columbus, and you can conclude that I was born in Ohio. So this is a correct conclusion, but the starting, some of the starting information was incorrect. I was not born in Columbus. Okay, so the idea is that you can have correct. There's a distinction between correct reasoning and then actually producing correct information. Okay, your proofs are based on the proofs that we write. We're going to assume that the information we're starting with are true. Everybody agrees upon these true statements, and then if we build off of if we have correct information, you use correct logic, then the conclusions that we draw will be correct statements. Okay. All right. So let's talk about section 2.1. We talk about statements. Statements. what is a statement? So 2.1. All right, let's call a statement is a sentence, because you know what a sentence is, right? Because I've had math classes, like particularly I've been teaching Math 1100, where I ask people to write their answer as a complete sentence, and Wes knows back there, and people struggle with what a sentence is. Okay, so a statement is a sentence. Now, this is kind of a transition from algebra-based math classes to proof-based math classes. So from usually above this level of math, there's going to be a lot of writing in math, and I'd be doing my homework when I was a math major, and people see sentences and are like, "What are you doing? That's not math. You got words all over your paper." Well, I mean, there's going to be a lot of mathematics, and most of mathematics is done with words and sentences and statements. Okay, so a statement, we write essays. A proof is an essay. So a statement is a sentence that is either true or is false. So a statement is a sentence that is either true, and I'll use capital T for true, or false, capital F. Okay, so we'll abbreviate, true and false, capital T, capital F. So not every sentence is a statement. Let me use some examples of statements. Example statements. The sky is blue. That's a statement, a sentence, and it's either true or false. How about this? 2 is an element of the integers. I mean, we have abbreviations, but it's still a sentence. You could actually write those words out. 2 is an element of the integers. That is a statement that is either true or false. All integers are real numbers. How would you read this sentence?
Rational numbers are a subset of natural numbers.
So the rational numbers are a subset of the natural numbers. This is a statement because it's either true or false. 4 is an element of the empty set. That is a statement. If x is an integer, then x squared plus x plus 3 is odd. So this is an example of the type of statements that we'll eventually be able to prove. So this is kind of where we're headed. We know what integers are. We'll talk about what does it mean for an integer to be odd or even. But this is an example of a mathematical statement that will be in the scope of this class. So I said these are statements because these are sentences that are either true or false. So let's figure it out which ones are true and which ones are false. Is the sky blue?
Yes.
Yeah, I mean, let's not be physicists here and say, well, technically it's just refracting light, and the sky actually doesn't have a color. I mean, okay, sky's blue. Okay, so true. All right, so is 2 an element? 2 is an element of integers. True or false? True. All integers are real numbers. True or false? True. The rationals are a subset of the natural numbers. False. 1/2 is a rational number. 1/2 is not a natural number. 4 is an element of the empty set. False. If x is an integer, then x squared plus x plus 3 is odd. Or true and false. There's a hint. It's either true or false. So, this is actually a true statement. So if you think about it, let's make a problem. Think of an easier problem. If you add two even numbers, what do you get? Even or odd? Even plus even is even. What about odd plus odd? Even. Okay. What if an even and an odd? Yeah, those together.
Odd.
You get odd. So think about this. What if you square an even number? What do you get? Even. What if you square an odd number? What do you get? Odd. So whether you start out with an even number or an odd number, when you add these two parts together, they're going to have the same parity. They're either going to be both even or both odd. Right? If x is even, x squared is even, and x is even. So even plus even is going to be even. Right? If you start out with an odd number squared is odd plus odd is even. So no matter what I plug in for x, as long as I start out with an integer, these first two summands are going to be an even number, and an even number plus 3 will always be odd. So it's actually true. This is actually a true statement. So we'll, and the proof I just gave you, kind of talk you through, is an example of proof we'll do in this class. A proof by case. We'll look at the different cases. Well, what if x is odd? What if x is even? And we'll deduce this is actually a true statement. Okay? So these are examples of statements. A sentence that is either true or false. So I said not every sentence is a statement. Our definition of a statement. Let me give you examples of sentences that would not be statements. About how are you? This is a sentence. It's not a statement. Choose any integer. It's a sentence, not a statement.
So commands and questions would not be considered statements.
Well, from example of size 1, I mean, so if I just, is there such, could you have a question that's a statement? Is he asking, are all questions ruled out as statements? Yes. You can't have a question that's a statement. Choose any integer. Yeah, so you're saying this is a, giving something a directions or a command, you cannot, that is not a statement. Choose any integer. One common sentence that's used a lot in mathematical proofs, let epsilon be greater than 0. You know, I've written so many proofs where I start off with, let epsilon be greater than 0. And you get the, I guess if you take advanced calculus, or what we call it, analysis 1, something like that. I mean, there's these proofs. Let epsilon be greater than 0. That's not a statement.
If you just wrote epsilon is greater than 0, would that be? That would be a statement, wouldn't it?
Is it? What is epsilon? You haven't defined epsilon. So it's not a statement. I can't prove that epsilon is greater than 0. It's close. It's closer than this.
Mm-hmm.
We'll talk about that in a minute. So it depends. In that case, it would depend on what epsilon was. Okay, that we call those open sentences. Okay, so how about solve 2f equals 10? And again, it's just a command. It's not. This is not. You cannot prove that this is a true statement, or it's not a true statement or a false statement. It's a command. How about this? So this is on the order of what the question you just asked. 2x is even, clearly, right? It's a multiple of 2, right? So this is a true statement. Is this true? Not necessarily. Why not?
No more. Go ahead.
You have just rational numbers, and it could be 1.5.
Sure. What if I put a half in for x? If x was a half, then 2 times 1/2 is 1. 1 isn't even. So this is not a statement because you cannot tell me, wait, we don't have enough information about x. Okay? This is not a statement because you cannot say this is always true or always false. A statement is, I say it's either true or false. It's always true or always false. There's no gray area. Okay? It's not, well, sometimes it's true, sometimes it's false. That's not a definition of a statement. It's either true or false. So this is what we call an open sentence. It's open because it could be true, it could be false. It depends on the variable in the sentence. Okay? So if I give you more information, like if I say x is a natural number, then it would be a true statement. For any, if I plug in any natural number for x, then it would be true that 2x would be even. Or even integers. If I said x is an integer, 2 times x, 2 times an integer is always even. Okay? But as it is, this is we call it an open sentence. Okay? Let's see. There's actually some other good examples in the book. So some statements in the book. 2 is an integer. Square root of 2 is not an element of an integer. 5 equals 2. Is that a statement? 5 equals 2. It's a statement. It's a false statement. The integers are a subset of the natural numbers. Okay, again, it's a statement, but it's false statements. Not statements. Add 5 to both sides. That's not a statement. 42. This is like my Math2200 students. Now, how many handshakes were there? I had the problem last week. How many handshakes were there? 55. Okay, that's not a complete sentence. Okay, I asked my students, answer the question with a complete sentence. 42. All right. What is the solution of 2x equals 84? I mean, that's again, it's a question. It's not a statement. All right. Some common notation. We often use capital letters to stand for sentences. I mean, mathematicians are kind of a joke about they're lazy. They come up with notation for everything, so it's just easier to write your proofs. You just call a whole sentence a letter. Okay, so that's an example. We often use letters like capital letters like capital P, capital Q, capital R, and capital S to stand for specific statements. Okay. So do you know why we use P, Q, R, and S for capital or for specific statements? I mean, I don't know. I was kind of curious if you knew. I don't. That's a bad joke.
Is it be like for premise?
Well, I think some books I've seen it calls instead of statements they use the word proposition maybe. So maybe capital P for proposition. But what happens in math is the first guy does it and it works. So let's just not just kind of follow suit. A lot of things like why do we use X all the time in math classes? Well, some of the first mathematicians who wrote algebra books use letters at the end of the alphabet for variables, and they use letters at the beginning of the alphabet for constants like A, B, and C. So first people did it and it worked good. So we just kind of it's not broke, don't fix it. So, but anyway, so you'll see this again. You get used to this. In math you don't learn anything, you just get used to it. So P, Q, R, S will be common. And sometimes it'll just seem weird to you not to use these things. Like it'll seem weird to you not to use n when referring to a natural number. It's like let n be a natural number. It's kind of like you just see it so many times. But there's no rules against using different letters. All right. So P, Q, R, S stand for specific statements. So like for example. We say something like P is the sentence f of x equals x cubed plus 5x squared plus 2x plus 1 has no positive real zeros. Okay, so this is a statement. This function has no positive real zeros. It's a statement because it's either true or false. It happens to be a true statement. But you can imagine why you might want to just call that a letter instead of, if you're trying to prove a statement and write a proof, instead of referring back to it or rewriting the sentence or restating the sentence over and over, you can just say, okay, well, statement P is, we're trying to prove statement P, and so that's an example where you might, it's like a shorthand. You just call a whole sentence with a letter so you can not have to keep referring to it, actually reading it over and over. Here's a statement. Square root of 2, the square root of 2 is irrational. I'm going to call that sentence Q. Okay. Is that true or false? True. You guys believe it's true, right? Because your calculator says so. But could you prove it?
Yeah.
You proved it last year? Huh? Well, it's still true this year. We use a proof. You probably use a proof by contradiction. Prove square root of 2 is irrational. It's kind of when you go on to you guys go on to graduate school or something. Often graduate programs make you do like in mathematics, you have to do like an oral exam where you stand on the board and they say prove this, prove this, prove this. This could be like a warm-up question. Prove that square root of 2 is irrational. And stand up here and just prove it. Okay, how about this sentence? I'm going to call this sentence R. If x is an integer, then 2x is even. So you see, it's different from when I wrote it originally. I just wrote this phrase: 2x is even. 2x is even is not a statement, but with this information, if x is an integer, then 2x is even. Now this is a statement because this is either true or false. This is a true statement. Okay, so it's true all the time. If x is an integer, then 2x is even. So even though this sentence involves a variable, it's still true all the time. Some sentences are true depending on the variable. Okay, and I said we call these open sentences. Here's an example. Well, another thing, you might even, book says, oftentimes you might even call it, instead of calling this capital R, I might call it capital R of X. And it's kind of like the function notation. It means that there's a variable in your sentence. And so this sentence that kind of might depend on this variable. Okay, in this case it's true all the time, but some sentences have variables and the sentence is either true or false depending on the value. Okay, so if a sentence, it's called P, contains a variable such as x, we can denote it as P of x. Okay, so it's kind of like it's depending on the truth or false. The truth of this statement depends on the value of x. Okay, so here's an example. P of x, x squared is non-negative. X squared is non-negative. Is this a statement? Is this true or false? X squared is non-negative. Everybody say it's true? X squared is non-negative. So it's true? Do you guys think it's a statement? It's a true statement. What do you think? Yeah, well, I mean, Do you think there's maybe an x of I for x I could plug in to make this non-negative, make this negative? Well, you guys have been shackled to the realm of real numbers. So expand your mind and think about complex numbers or imaginary numbers. I, yes. Think about the imaginary unit I. I stands for. So this is true sometimes. This is true. This is true for real numbers. For, let's say, for x equals 3, right? X, so 3 squared equals 9. But this is false for x equal to I, which is the square root of negative 1. I didn't say that x can't be a complex number or imaginary number. So the square root of negative 1 squared is negative 1, which is negative. So again, this is not a statement because it's not true all the time, and it's not false all the time. It depends on the value of x. So we call this an open sentence. Okay, so this is not a statement because its truth depends on the value of x.
So if they said x squared is non-negative given x is an element of all real numbers, would that be considered?
That would be true. So it would be a statement. So yeah, right. If I added a further sentence like given a real number x squared is non-negative, that would be a true statement. It would be a statement and it would be a true statement. Okay, so like I said, so a sentence such as this is called an open sentence. So the question, if I said, is this a statement? You'd have to say, no, this is not a statement. You could further add, it's actually an open sentence, But if I ask you a yes or no question, is x squared is non-negative? That is not a statement. It's an open sentence. Okay, any questions? Okay, so that is all of 2.1. Homework from 2.1. There's only 15. There's 15 problems in section 2.1. Okay, they're just sentences, and all you have to do is to figure out whether they're statements or not. Okay, so I want you to look at all 15 of the problems from 2.1. Okay, and half of them are in the back of the book, right? More than half. So, but again, I want you to think about it, not just look at look up in the back of the book. Okay. Let's see here. Wasn't sure how much time the quiz is going to take, and then 2.2 is kind of a long. It's a longer section than